This is Samadhya from VBind Education Technologies, Mumbai. And as you know, VBind brings industry experts live into your classroom. And for today's session on algorithm designing, we have got Ms. Mansi Gupta joining us as the speaker for today. Ms. Mansi Gupta is a data scientist with the world famous company LinkedIn, and she is here to educate us on what algorithm is all about, what algorithm designing and analysis is all about, and how LinkedIn uses these technologies for its own purpose. So without any further delay, I invite Ms. Mansi Gupta to take over. Over to you, Mansi.
Hey, hi everyone. Good morning. I'm going to talk about how search works. So whenever you type something on Google search and hit enter, so what happens on the back end? So I'm going to talk about very basic algorithms behind search. So a little bit of my background. So I was in college as you guys just a year back, and I passed out from BITS Pilani. Then I joined LinkedIn in the search team. So I have a couple of years of experience in search. So yeah, so yes. So as you all know that we are like big data is a buzzword as of now. We are surrounded by a lot of data on the internet. So today hundreds of GBs of data is generated every second. Whatever you do, whether you put a status on Facebook or you send a message on WhatsApp, it is all contributing to this data, this huge data generation, right? And not only what you do, but also companies, like even if you open your smartphone which is connected to internet, companies track your activity like each second. So they track your each impression, each click, what post you are reading for a long time, like everything is tracked. So all this tracking data, all the millions of videos on YouTube, millions of articles on the internet, all contribute to this big data. But the thing is that we have so much data, right? If we don't manage this data properly, then like it's going to be a huge problem. So imagine you being in a big library with thousands of books, and the library is not organized, it's not cataloged at all. You will feel totally lost. You would not know like what to do, where to look for a particular book. So but the web is huge, like it's like millions of these libraries. So today there are around 4.72 billion pages on the web. So that is a huge scale. So without retrieval capabilities, without search capabilities, this data is not of any use, right? So it's like so suppose you don't have Google search at all. How would you go to a particular websites? You would have to remember the names of URL and stuff like that, right? Which is like very inconvenient. So that is why search is very important. Yeah, so at this point, I would like to say that if any college thinks that I'm going really fast, the moderators can interrupt and like let me know. Otherwise, for the questions, I'll keep around 10 minutes in the end so that we can take questions. So yeah, so this is a small video telling about how search works. Let's have a look at it. So can people hear it?
Sorry to interrupt, Mansi. We're not able to hear it.
Yeah. Okay. So what I'll do is I'll just take out my headphones then, maybe. If you're not able to, just let me know.
I'm an engineer in the quality group at Google, and I'd like to talk today about what happens when you do a web search.
So is it audible? Hello?
Hello. Yeah, I request you to please stop the share. And once you start the screen sharing again, there is two options for share audio through computer. If you can just stop the share and click on share screen. At the belowmost panel, there is share computer sound and optimize for full screen audio, video.
Got it, got it, got it.
Just click the check boxes and then go for this.
Got it. Yeah, so is it audible now?
Hi, my name.
Not yet.
Not audible?
Not audible on my side.
Okay, okay, okay. Let's leave it. It's okay.
I think the early option was working fine when you just removed the headphones.
Okay.
So we may try that.
Okay, okay, I'll try that.
Hi, my name is Matt Cutts. I'm an engineer in the quality group at Google, and I'd like to talk today.
So is it fine? Hey, by the show of hands, is it fine?
Yes, we are able to hear this.
Okay, okay, awesome.
What happens when you do a web search? The first thing to understand is that when you do a Google search, you aren't actually searching the web. You're searching Google's index of the web, or at least as much of it as we can find. We do this with software programs called spiders.
So the thing here to note is that Google search does not actually search the web. It indexes the web and then searches it. So let's see what is the meaning of index now. So all the data is stored on Google's own computers.
Spiders start by fetching a few web pages. Then they follow the links on those pages and fetch the pages they point to, and follow all the links on those pages and fetch the pages they link to, and so on, until we've indexed a pretty big chunk of the web, many billions of pages stored across thousands of machines. Now, suppose I want to know how fast a cheetah can run. I type in my search, say cheetah running speed, and hit return. Our software searches our index to find every page that includes those search terms. In this case, there are hundreds of thousands of possible results. How does Google decide which few documents I really want? By asking questions, more than 200 of them, like, how many times does this page contain your keywords? Do the words appear in the title, in the URL, directly adjacent? Does the page include synonyms for those words? Is this page from a quality website, or is it low quality, even spammy? What is this page's page rank? That's a formula invented by our founders, Larry Page and Sergey Brin, that rates a web page's importance.
Okay, so the point here was, yeah. So the point here was that Google uses something called crawlers. It searches its whole index and it takes all the documents, and now it uses them to give you search results. Okay, so let's see what happens when a Google or any other search company has all the documents you need. So what happens after the documents are collected? They are stored in something called as search index. So we'll have a look at what is search index. So first let's see what is a query. So query is something what you type. So the raw query is something what you type in the box, right? So at the back end, at the Google or any other search company, they have this concept called Boolean query. So what Boolean query is, so let's say you are typing two terms, term 1 and term 2, right? So how Google interprets it, so there are Boolean operators, and, or, and, not. And means that the page should have term 1 and term 2 both. So this is the default behavior, right? So let's see how Google uses it. Okay, let me go to a different screen. Yeah. Yeah. So let's say I search for these two terms, Tahiti and Hawaii. These are two islands in US. So all the results you see here on this page, they would have both the terms. They would have both Tahiti and Hawaii, both Tahiti and Hawaii. So if you go to, let's say, even if you go to, let's say, page 8, so in all the pages you would see both these two terms are highlighted. So by default, the behavior of search is and. So if you search for two terms, it's term 1 and term 2. So, but you can actually write, so what you want, so let's say what you want is you want pages which have either of these terms. It's not important for you that both the terms are present. Okay. So you particularly ask Google, you write this or. So all the pages you see here would have either Tahiti or Hawaii. So see, this is a Wikipedia page for just Hawaii. This is a Wikipedia page for just Tahiti, right? So this is how you can actually give keywords to Google. And then the third part is not. Okay. So let's say I search for university on Google. So it would give me a lot of universities, okay, and it would give me a lot of Bangalore universities. But let's say I don't want universities from Bangalore. So what I just do is I just put a minus sign against Bangalore, and it would give me, it doesn't show me now any Bangalore universities, right? So this is how these operators work. So let me go back to my slides. And we will see actually that how these are implemented in the backend. So yes. So also, this was, so we saw that and is a default behavior, or is something which you can specify, and this minus is something which is interpreted as term 1 but not term 2. Also, in this or Boolean operator, let's say you have it also searches for synonyms. Let's say you type a word, let's say happy, okay, so Google search in its backend would also consider all the synonyms of happy, like say gay, amused, and things like that, okay. So in the backend it would implement or. So let's see how these operators are implemented and how Google searches it. So there is a index called search index. Okay. So if you are given a lot of documents, let's say in the form of books, how would you search it? Let's say you are given some words, okay. So you would, so a bad way would be to open all the books, search for that particular term, and if it is not found in the first book, search the second book, and so on, right? So if it is a huge book, it is a very difficult task. But many books you would have seen an index at the end. So what that index is, so it would give you a term, and then at the side it would give you the pages on which that term occurs. So it makes it very easy for you. You can just go to those pages and find whatever you are looking for, right? So similar is the concept behind the search index. So it is called inverted index. It is called an inverted index because it's not that you are given a document and the list of the terms. It is actually you are given a term and the list of the documents. It's exactly like an index behind a book where you are given a term and the list of the page numbers, right? Okay, so let's see how the inverted index looks like. So on the left, you can see that there is this is like, let's say all these are my documents. These are all the documents I have for now, and these documents are given an ID 1 2 3 4, and these documents have some text, okay. Now I want to search for some particular words. Let's say I want to search for summer. Okay. So on the right is my inverted index. This is how the inverted index looks like. And this would have all the terms and a list of all the documents. So let's say summer is present in the document 1, 2, 3. Picnic is present in the document ID 2. Mangoes are just present in the document ID 1. So even if I don't have the list of the text, even if I don't have the left table, from the right table, I can find out which documents to look for, right? And it makes things for me like pretty easy. Now, just a second. Yeah. So now this is the right side is which is called an inverted index, and how it is stored in the computers of Google, or say for LinkedIn and LinkedIn search and so on. So let's try to find out what data index. How can you repeat this? Let's say you are given a term. Let's say you are given a term summer, and you have to find out. So you have to store a list of documents, right? So it can use. So you can the first thing that comes into mind is array. You can store all these document IDs in an array. But here an array is not suitable, because let's say a new document comes that also contains a term summer, and you have to add this document. So in array, the memory allocation is a huge. You have to allocate memory to document comes, right? So what we use is a linked list. Okay, so we have a sorted. So first of all these document IDs are sorted. Like again, summer, I would store 1, 2, 3 and not 3, 2, 1. And if a new document comes, I'll just append that document in the linked list. So adding a node in a linked list is pretty easy, right? And as the new document comes, their IDs would be increasing, and I would keep appending it at the end of the linked list, right? So these are called posting list. All the lists you see there, these are called posting list. So this whole data structure is actually a hash table where the terms are the keys and the values of these posting list, right? So if you remind yourself, the complexity of a hash table for retrieval is O of 1. So let's say I'm searching for 2 and go from for mangoes, which is just 1, the first document, and in one the list for some, which is 1, 2 and 3. So I'll get these two lists. I'll see what common document I have in these two, and I'll just retrieve them, right? So the common document which I have is 1, and I'll show the user, right? So yeah, this is the posting lists are implemented using linked list. And no, it is not an array, because the memory allocation in array is like much better than in a linked list. And all these the terms are hashed, and the whole structure is a hash table where the key is the term and the value is the linked list, right? Okay, so I guess this much is clear. Now let's see how so I talked about Boolean queries, right? So let's say I'm searching for 2 terms, and then let's see how or and are implemented. Okay, so let's say the term 1 so the posting list for term 1 is, let's say, 1, 2, 3. Sorry, is anyone speaking something? Okay, yeah. So so the posting list for term 1 is, let's say, these documents. So term 1 is present in document 1, 2, 3, 5 and 6, and as I told you, they're stored in a sorted order. And then term 2 is, let's say, present in these documents 1, 3, 4, 5, 1, 3, 4, 5, 7 and 8, right? So I got these posting list in an O1 time from this inverted index. Now how do I combine them? So if I'm using a Boolean OR operator, I'll take a union of these two posting lists. So I want, so or means that either term 1 is present or term 2 is present or both of them are present, right? And if I want an intersection, if I want an and on these two terms, that would mean that I want only those document in which both the terms are present. So I would take an intersection of these two posting lists. So like it's a very common algorithm to merge two lists to sorted list, which is so, and the time complexity of that algorithm is O m plus n. So you can go back and look at how this algorithm exactly works. So in o m plus n, m is the length of the first list and n is the length of the second list. So the maximum time it can take is, the maximum number of iteration it can take is m plus n. So the time complexity is O m plus n. So let's look at quickly that how OR works. Okay, so we have these two sorted lists 1 2 3 5 6 and 1 3 4 5 7 8. Okay, so we'll have two pointers. One would point at the first list and the other would point at the second list. So we see that 1 and 1 is common, right? So okay, let me write it here. So I'll just copy 1 because 1 is there in both the list. Now I'll move my pointers. So my first pointer is at 2 and the second pointer is at 3, right? So I'll just write the smaller of these two. Okay, so since 2 is smaller than 3, in my union I'll just write 2. Okay, now since I've written 2, I'll move this pointer, the pointer that was at 2, I'll move it at 3 here, and this pointer I don't move because I have not yet written 3, right? So then I see that both these pointers are at the same numbers, then I'll write 3. Now since I've written 3, I'll move this pointer at 5 and I'll move this pointer at 4, right? Now I'll take the smaller of these two. So whenever the pointer are at the same number, we take that number. If the pointer is at the smaller number, we take the smaller number. So now the pointer is at 5 and 4. So I take 4 and I increase this pointer to be at 5, but I don't increase this pointer. Now you will see both the pointers are at 5. So I'll take 5. Now I'll increase both the pointers because 5 is already taken. I move it to 6 and 7. Now I'll take the smaller one, which is 6. And like there is not, so I was supposed to move this pointer, but we have reached the end of the list. So I'll just copy whatever is there in the second list, right? So now these are all the documents which are in the union of both of these lists, right? So this is how the or works. So now we have all the documents which have both these terms, and a very similar algorithm is for AND. So I'm not going into that yet, but it is very similar with the same time complexity. So let's say we have a third term. So what we'll do is, let's say we have a term 1 or term 2 or term 3. So what I'll do is I'll take this posting list which is of term 1 or term 2, and I'll take the posting list of term 3 and I'll do the same thing what I did with term 1 and term 2, right? So this will give me the document, all the documents which have either term 1 or term 2 or term 3, right? Yeah. So this is how this merging works. Yeah, this is the algorithm I explained. Yes. So so now we have all the documents we need, right? But we just have a list of documents. We don't know that which document is important. Let's say a Wikipedia entry is much, say, given more important than a news article. So I want to rank those search documents, right? So on a higher level, there are two steps to search. One is retrieval and the other is ranking. So what we saw right now was retrieval. So what retrieval means is just getting all the documents. You just have all the documents. You don't know what order they are to be shown to the user. You just got them in the sorted order of their document IDs, right? So now you will need something to like sort it in the basis, on the basis of what you think is important for the user. Okay, so let's take example. Let's say you are querying for a single term summer. Okay, so here how will the retrieval look like? Okay, so ranking or scoring, they mean the same thing. It's just scoring all the documents you get, right? So retrieval is just getting the posting list, and scoring means scoring them by scoring the documents, right? So for since this is only one term, no merging or anything like that is needed. Now for scoring you can have different algorithms. So let's say I use a very simple algorithm that I'll give those documents more weight which would have summer more number of times. So I just score by frequency of the summer in frequency of the term summer in the descending order. So let's go back to our inverted index. So let's see, summer is appearing in document 2 and 3, and document 1 has summer 2 times, document 2 just has 1 time, and document 3 has 1 time. So my algorithm decides that 1 is most important, right? So I'll show 1 at the top, and second and third I can show like anywhere randomly. So this is how a simple scoring algorithm would work, but actually in reality this is like a fairly complex algorithm. Now let's say I query for 2 terms, summer and hot. So what my retrieval would look like is, it would get me the documents which have both summer and hot in present in them. So this is what my retrieval look like, and it would take intersection of 2 posting lists. And how my scoring would look like, let's say this is my scoring algorithm, that I take the frequency of the first term, and then I add it with the frequency of the second term, right? So let's say if I consider from this R inverted index, if I consider summer and hot, okay, so yeah, so I take the posting list for summer, which is 1, 2 and 3. Then I take the posting list for hot, which is just 1, and I take the intersection. It's giving me just 1 document. So like here there is no concept of scoring, but let's say if we have more than we have say thousands of documents, so how would I score it? I use a simple frequency term frequency addition algorithm. That's all, right? So so let's say this algorithm, frequency of summer plus frequency of hot, for this document 1, it would give me a score of 3. So for example, there is some other document which has a text which just has a text summer is hot. So that document would give me the score of 2, frequency of 1 for summer and frequency of 1 for hot. So yeah, so I would rank that document. I would rank the document number 1 first, and then I would rank that document with the score 2. So yeah, so the takeaways from this is, on a high level, search can be divided into 2 parts. One is retrieval and the other is scoring. Retrieval is getting all the relevant documents for the given query terms, and scoring is scoring those documents on some particular algorithm, right? So yeah, these are the two things to remember in search. So let's see what next. So let's say you give this query PayPal Israel on Google, right? So Google gets all the documents and it sorts them also, but now it only has the document IDs, but it can't show you those numbers, right? There would be some IDs, but what exactly does it show to the user? So what Google shows is, it shows a title, it shows a snippet, and it shows a URL, right? So it on the search page, it shows these 3 things, right? So if you click on that link, it would go to link of that particular website, right? But on its own page, it has to show these 3 things: title, snippet, and URL. Now inverted index doesn't give any information about that. Inverted index just tells you that these terms are present in these documents, that's all. It doesn't give any information about other things about that document. So these things have to be stored. So once we have all the documents we want to show, now we'll have to somehow fetch title, snippet, and URL, right? So how Google stores it is something called as forward index. So what we were talking about that time is inverted index. Now we want the forward index. Okay. So forward index contains all the terms which the results page shows you. Okay. So on the left side, this table, you can see the forward index. So again, these are the document IDs, and let's say Google wants to show you title and snippet, and these are the title and snippets of this particular document. And so I mean, forward index is really simple. It's just, you can say you can just consider it a mapping of document ID and whatever you want to show. So it's, you can consider it as at a simple, as like a simple array on which, let's say if the document ID is 3, at the third position title and snippet for document 3 is stored. So it's really simple. So uh, so this itself on the left side is the forward index, and on the right side is the inverted index. So the thing to be noted here is that all the text of the document against anything which Google is matching, all that is stored in the inverted index. It need not be stored in the forward index. Forward index only contains things that you need to that are needed to show a user on the first page itself, right? Okay, so yeah. Now also let's go back to inverted index. And so the inverted index is like the base of search, right? So all the search operations happen on the inverted index. But as we talked, that the Google index is huge. It has 4.72 billion documents. So obviously, like, it is very obvious to imagine that it is TBs of data, and it won't fit into one computer. So now we will look at how we break that inverted index into multiple machines. Okay. So so we have to so what we look at is, we have to have some strategy to break this index into multiple machines, to take the results from the individual machines and to combine them in some way, right? So so the index has to be partitioned in some way to different machine, and each partition is called a shard. Okay. So so this is how the system looks like on a very high level. So there is no need to get intimidated by this diagram. It's like really simple. So what we have is it is a master slave configuration. So what happens is, this is the front end. Okay. So front end is where the user enters the query, and it goes into one machine. Then this machine distributes it to multiple machine. This machine distributes the query to multiple. Sorry, is someone saying something?
Sorry for the interruption. A college has unmuted themselves.
Okay.
I've muted them
Do
again.
they want to
I
say
request the
something?
colleges to do not unmute yourself.
So if someone thinks I am going really fast, they can stop me. Please feel free to stop me. Okay. Yeah. So yeah, what I was saying is that the query is, the front end gives a query to a machine, which is called the master machine. And this master machine, which would distribute it to many slave machines. So these slave machines, which would actually have your index. Okay. And then these slave machines would return you some partial result, and the master machine would combine that result, and it would send it to the front end. So this is not just for search. This is a very basic distributed computing concept, which is used in so many different things. It is so, whatever you do on, let's say you open linkedin.com or you open flipkart.com, so obviously that site is not stored on one computer, right? So many things are like distributed, and this is a very basic distributed framework, distributed computing framework. So if you in future, if you learn about parallel computing, or if you work in some company, this framework would be used everywhere. So now let's come back to search. Okay, so okay, let's see how the document is how the inverted index is partitioned. Okay, so before that, uh, the front end, so you are passing the query in the front end, right? And you, in the front end, you also give the total number of documents you want to get from the index. So let's say you are hitting the Google search, and let's say you want 10 documents on the first page. Okay, you just need, let's say in this case, you just need 5 documents. That's all you care about. So what happens is, the front end would send the master machine two things. One is the query, and the other is the number of documents you want, right? So, and the master document would pass these two parameters to all the machine. So all these green arrow you are seeing, this is like master machine passing all the parameters. Okay, so so these all the shards would return. So let's say master machine passes 5. Okay, so now what happens is, all the shards, they return 5 documents to the master machine. So now but like some shards might not have, some shard might have just one document, they don't have any other document matching that particular query. Okay, so that is why I've written less than or equal to 5, right? So now the master machine receives 25 documents, right? So okay, so let's see how the index is partitioned on the slave machines. So I'll come back to this whole cycle, but first let's see that how the index is partitioned. So the index is document partitioned. So that can be two types of partitions. One is term partition and one is document partition. Okay, so okay, so let's go back to the full index. Yeah, so on the right side is the inverted index, and we are talking about partitioning of this index. So one thing is, we can partition, let's say there are around 15 terms in this inverted index, and let's say first 7 terms I keep in one machine, and the last 8 terms I keep in another machine, right? This is one kind of partitioning I can make. And the other kind of partitioning I can make is this kind. So where I do not partition terms, all terms are there in all the shards, but what I partition with is the document ID. So the length of posting list would get reduced in all the shards. So let's say for this particular inverted index, the example inverted index I'm showing you, let's say there are 2 shards. Okay, and in the first shard I have 1 and 2, and in the second shard I have 3 and 4 as documents. Okay, so forget about the query as of now, just look at these tables. Okay, so all the terms which have 1 and 2 which have 1 and 2, all the terms of document 1 and document 2 are there in first chart, and all the terms which have of document 3 and document 4 are in the second chart. Okay, so I talked about 2 strategies of sharding. One is by term and one is by document. So but we used document sharding, we used document based partitioning and not term based partitioning. So why do we do that? So one thing is that, let's say if you issue a query, okay, and so let's say my query here is hot and summer. Okay, and I do a term based partitioning. So for term based partitioning, let's say I divide these first few terms in the first chart and the second few terms in the second chart, right? And let's say something happens and there is some power failure in my first machine. Okay, so see here, summer and hot, both of these terms are in first machine. Okay, so this way my system wouldn't return anything at all. It would return empty queries. Okay, and if I do partitioning based on documents, what would happen is, so let's say one of my, let's say this machine fails. Okay, so even if this machine fails, I can hope to get at least some results from the other machines. So when I do document based partitioning, um, the first machine, let's say it has 1 to 20 documents and it fails, so it's okay, it would not return anything from 1 to 20, but at least I'll get results from 20 to 100. But if I do term based partitioning, what will happen is, if the terms I'm searching for are stored, let's say I search for just one term, and all the documents for this one term are stored in the first shard, like then it's a huge problem for me. It would not return any result, right? So this is one of the reason we use document based partitioning. There are another reasons also, but they're a bit complicated, so let's not go into that now, but this is like the most basic reason we use document based partitioning. So yeah, to look at it again how it works, just to make sure that everyone is clear about it. So the front end requests the master machine to give a query, and it gives a number of documents it is expecting. Okay, so so let's say the query is very unique. Okay, so you are searching for a very unique thing, which corpus, in the corpus means the collection of all the documents. So in the corpus, let's say only one document has the term. Okay, so obviously in that case it would only return one document, even if the front end is asking for 5 documents. So which is fine, the front end can only give a upper limit of the number of documents it is expecting. Okay, so let's say here in this case the upper limit is 5. So the front end sends to the master machine to, again, two parameters, query and 5. These two parameters master passes to all the machines. Okay, now what first machine would do is, it's like a mini collection of documents. First machine is the search index in itself. Okay, it's a subset of all the documents we have. Okay, so the first machine would look in its own mini collection, and it would give you let's say 5 documents, or it would give, let's say it gives you only 3 documents. And similarly second machine would do the same, third machine would do the same, and at maximum they would give, let's say all machines have at least 5 documents, at maximum they would pass 25 documents to the master machine. Now as the inverted index is located in the these small slave machines, so the part which we were talking about, the retrieval part, would happen in this phase. So this part what we talked about here, that yeah, so let's say we have mango and summer and the posting list, and this part, right? Yeah, this part, the merging part, where we get posting list for term 1 and we get posting list for term 2 and merge them in some way. All these things would happen in the slave machines, because this is something which has all the the information about the index. Now slave machines do not do any scoring or anything. Slave machines just pass these 5 documents, the top 5 documents, to the master machine. Now the master machine has 25 documents. Now is the time for scoring. Now the master machine, so the strategy we talked about for scoring was simple. If there are more terms in the document which are also there in the query, give it higher score. If there are less query terms in the document, give it lower score. So now the master machine would rank these 25 documents and return top 5 to the front end, right? So this is how the distributed part of search works. Like again, it's a very high level picture, but this is like the basics of it. So Yeah, so as I talked about, so this is a sharded index. So we have divided our index in a way such that first two documents are there in shard 1, and so we had only 4 documents in our index. So out of these, first 2 are there in shard 1 and 3 and 4 are there in shard 2. Now I am querying for hot summer, and the total number of documents which I require is 2. So now the front end sends hot summer and 2 to the machine, okay, which gives it to the shards. So each shard receives these 2 parameters, and the first shard looks in its index, what can it return? So it sees, so let's say the query is hot or summer, okay, so it can return you either of the documents which is hot, or the documents which have summer, or the documents which have both, okay. So the first index, what will it return? It will go at summer, it will look that okay, it has 2 documents, 1 and 2. Then it will go at hot, it would look at the posting list of hot, which is just 1. It would take a union between these 2 posting lists. Since it is or, that is why I'm taking a union. The union of these posting list is 1 comma 2, okay. So this particular shard returns to the machine this post list 1 and 2. Let's see what the second shard returns. In the second shard, it would look at summer, it would see the posting list is just 3. Then it would look at hot, it would see again the posting list is just 3. It would take the union between 2 posting lists, which is 3, and it would send 1, 2, and 3 to the again to this machine, okay. So the first shard sends 3, the other shard sends, first shard sends 1 and 2, the other shard sends 3, and now the machine has 3 documents, 1, 2, and 3, okay. So so now, but the total number of documents needed are 2. So what this machine will now do is, it would rank 1, 2, and 3 according to some scoring strategy, right? And it will return to the front end whatever the first the top out of these 3, the top 2 documents it would return to the front end. So this is how the distributed part of it works, okay. Okay, so yeah, this is all about the parallel part. Now the other thing that I wanted to talk about is query expansion. So okay, yeah, so before that, let me share the browser. Yeah. So is my browser visible? Yeah, okay. Yeah, now it is okay.
Yes,
So okay, awesome. So see, so I talked about Boolean operators, right? Or and. So here we'll see using LinkedIn search where these Boolean operator, like we use it in day-to-day life without even realizing. Okay, so let's see. I search for bits. I searched for bits planning, and I hit the search bar. Okay, now what I want to do, what I want to see is that I want to filter. These are on the left side, you can see all the filters, okay. So let's say I just want to see my first connections, okay. I click on this, okay. So let's go at location, okay. So let's say I want all the people from Bangalore and I want all the people from Hyderabad. So I'll click on these two check boxes, okay. Now what I want to do is I just want people from people who are working in Amazon, okay. So see, so the thing to notice here is, in when I'm selecting multiple facets from this, when I'm selecting multiple checkboxes in the same filter, let's say Hyderabad and Bangalore, there is a or operator applied here, right? Because I would want people who are either in Hyderabad or in Bangalore. It doesn't make sense to ask me for people who are both in Hyderabad and Bangalore, right? So if you're selecting multiple checkboxes from the same filter, it would internally apply an OR operator. But if you select one checkbox from here and one checkbox from here, it would internally apply an AND operator. So let's say if I want all the people staying in Hyderabad and working in Amazon, what I'll do is I'll select Hyderabad from here and Amazon from here. Now it is internally applying AND operator. So here AND operator is applied across filters and OR operator is applied within the filter. Okay. So let's look at another similar example. Let's say on Flipkart, I search for mobile phone. Okay. And if I want to get all the phones which are either of Samsung or of Apple, but I just want them which has, let's say, 3 to 4 GB RAM. Okay. So I select Samsung and Apple, and I select 3 GB to 4 GB RAM here. So what it will give me is, it would give me all the phones of Samsung, it would give me all the phones of Apple, and which have the RAM of 3 GB, right? So here it is applying an OR operator here, because it is giving both Samsung and Apple, and it is ANDing it with, so from all the phones of Samsung and Apple, it is taking an intersection of the phones which have 3 GB RAM. So across filters it is and between the filters it is OR. So it is like, so when we are doing all these things, it is implicit in our minds, right? So to teach the computer to do things, we'll have to like tell them explicitly that put a OR operator here and put a AND operator across the filters and so on. Okay. So yeah, so I'll go back to my slides just a second. Yeah. So there are a few more concepts. Quickly I'll cover in 2 minutes, and then I'll take questions. So there is a concept of, once Google has the query, so whatever we talked about here, so let's say you issue a query of mango, just mango and not mangoes, but your index has mangoes. Okay, so it will not return any document, which doesn't make sense. You are okay in getting a document having mangoes here if you search for mango, right? So for resolving these cases, to give you like a good number of relevant documents, what engines do is they apply a concept called stemming. So what stemming means is that, let's say all these are similar words: govern, government, governed, governing. All these are stemmed to its root word, which is govern. Okay. So what would happen is, in the document, so if you are giving a query with the term governance, it would be stemmed to govern. Okay. And your in index also, instead of having the documents for all these terms, it would be, all these documents would be mapped to govern also. So let's say this has the document, the govern was present in document 1, government was in, say, document 2, 3, governance was present in document 4, and so on. Okay, so it would have another index with the stemmed, this is called the stemmed term. The reduced term is called the stemmed term. So converted index for this stemmed term would have all these documents 1, 2, 3, 4, 5. Okay, so what it means is that if I search for any of these terms, it would get stemmed to govern, and it would return all the documents. So even if I search for governance, it would give me a document which contains government. Okay, so I'll give you a demo. Let me talk about one more thing, which is synonym expansion. So this is similar to stemming, but here we were doing a kind of compression. Here we'll do some kind of expansion. So let's say you type a query, this slow router problem. but the Google would also search for synonyms of problem, which is say issue, troubleshoot, trouble, and things like that. Okay, so so when the query, when you issue a query, Google would look at all its synonyms and it would issue an expanded query to its index. So this expanded query would also have the synonyms. Okay, and again, so if it is searching for synonym, it would have the or operator. So either it can be issue, or it can be troubleshoot, or it can be trouble, or it can be problem. So if we find any of these documents, it's okay. So let's see how it looks like. uh, yeah, so just a second. Yeah, so I issue a Google search for govern. Okay, so look at the results it's given. It is look at the highlights govern. See, government is also that from govern, it's able to do that government word. Then governing also highlighted. So these are all the this is all due to stemming performed. Okay, so this is, and it gives you the stemmed form of these words. Say and I issue a search. So this, let's see what this stemmer gives us. So it's taking a lot of time, but with all these words, it would give one word, govern. Okay, and similarly, like you can do it with any other kind of words. Let's say I give walk, walking, walked, walker. So all these would be mapped to walk. Okay, so this is how stemming works. And another example of synonym expansion, let's say my query is this slow router problem. So see, it is also getting related words, issues, fix, okay, and troubleshooting here, right? For router, it is getting, it is giving me other related words like internet, connection, and things like that. So these things were not there in my query, but since Google is highlighting it, that means that it is able to recognize that I may be looking for similar terms, right? So what I talked about was like some basic concepts of stemming and synonym expansion, but like nobody knows like what exactly Google uses to expand this query and to score and to retrieve. But like these are like the very basic things to build, very basic search engine. So okay. Yeah, so that is what I had. Yeah, so this is what I have for now. Any questions? I'm done from my side.
Mansi, thank you for the wonderful session. So we have thrown open the forum for question and answers. The
Okay.
students can come near the screen and ask the questions, or they can use
Okay.
chat box which is available.
Okay. Okay. Uh, okay. So what you can do is you can also write my email ID, which is mgupta1410@gmail.com. And if the time does not permit now, you can just mail me your queries, and I'll be happy to answer. And for now, I am open to take questions for say 10
Mansi, if
minutes.
you can stop the screen share option, you'll get the question. The students have already started the
Okay.
question.
Okay. 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 Got it. Okay. So the question is, why does Google change its algorithm for page ranking? How the changes are made in such a big code? Okay. So this page ranking algorithm, I did not go much into it because it is very specific to, link-based searches. So let's say if you have a document and you want to build a search engine, you won't use PageRank, right? PageRank is used when like a lot of documents are connected with each other. So if there is a document which have many important documents pointed to that, that itself becomes an important document. And if that important document points to some other document, it increases the importance of that document, right? So in the retrieval, in the scoring part we looked at, so important documents would be ranked first. So something like that. This is like the basic behind page ranking. So Google, so as far as we know, Google is still using page ranking algorithm, but it's like there are thousands of things which Google does, okay? And uh, not there is not a single person in the world which is familiar with the complete stack, the complete search stack of Google. And like people would know different parts, like someone would be working on language models, someone would be working on query expansion, some teams would be working on, like, so there are different teams. Google search is like a huge organization in itself, right? So they would have modular codes. So modularity is the answer here. They would have, you can consider it as different, uh, modules for different parts which are combined together to power Google search. So no one in the whole world has the access to the complete stack. Even the engineers in Google, they don't have the access to the complete stack. Yeah. So the other question is, what is the technology stack of Google? Okay. So I don't know what is the technology stack of Google, but the basics which I told here, they are applicable in any kind of search. So I have worked in LinkedIn. I have not worked in Google, but because people are so familiar with Google search and they use it for like their day-to-day everything work. So I took Google related examples, but in LinkedIn, the technologies I can tell, the technology stack is called Galean, which is Galene. Okay, so you can go online and look at how it works. Uh, can you tell us what algorithms are used in LinkedIn? Uh, so LinkedIn has different verticals. Okay, they have different search verticals. So in the search bar at the left side, you will see there are different people search, university search, then company search, post search. There are like different kind of these verticals, and every vertical would have their own. There are three parts: indexing, retrieval, and scoring. So every search vertical would have its own. So there is this infrastructure stack called Galean, and it provides us APIs to implement these three parts: indexing, scoring, and retrieval. So every search vertical would have, according to its needs, it would have their own algorithms. And like it's not like common for everything. And so so yeah, the only thing I can tell is that it uses Galean as an infrastructure. And yeah, and for every vertical the algorithms would be different, and it uses some bit of machine learning also, which is like learning to rank, which is a huge area in itself. So yes.
I hope that
Any
answers
other?
your question. Any more questions from the students? The students can add LinkedIn specific questions to Mansi, or probably a hack to LinkedIn search or something.
Okay, so I would like to tell one useful thing, which would be of maybe of use to you guys. So there is this open source search infrastructure called Elasticsearch. Okay, there are a few more called Solar, Lucene, etc. But Elasticsearch is like very handy. So let's say you have 200 documents with you, and you want to make search capabilities in that. Okay, so Elasticsearch is where you will go. So if you know the basics which I told you today, like that is enough to get started with it. Okay, you don't even need to know the parallel or distributed concepts which I talked about. You just need to have a basic understanding of what are Boolean queries, what is inverted index, and things like that. So yeah, this is of something which is of immediate use to, which might be of immediate use to you guys. You can maybe try it with help of your teachers, or you can maybe try it on your own. And yeah, you can write it in your resume also that you worked on Elasticsearch, you made a small project. If you have a website and you want to build some search functionality in it, people like generally use Elasticsearch for that. Yeah.
Any
Any
more
more questions?
questions? Any students want to come near the screen and ask the questions directly to Mansi?
So if you're feeling shy of asking me, you can always mail me. Okay, so there is one more question. How is machine learning used for search? Okay, so yeah, there are algorithms called learning to rank, and so what they do is they track whatever people have clicked in past. Okay, and they extract features. If you know about a bit about machine learning, so so what it does, it takes some training data, and then it uses that, it builds it model using that training data, and then this model it uses for like future scoring and all that. So in the scoring part, so let's say LinkedIn showed me, let's say 15 results, okay, and I clicked on, I don't like first 4 results, and I clicked on fifth result, okay. So it gives an indication that um, fifth result might have been better than the other 4, and LinkedIn's algorithm might be doing something wrong. So all these clicks are used as training. So at the back end, so let's say it's a people search and I'm looking for people on LinkedIn, and let's say I type for Mansi and there are 10 Mansis that come under my search results, and I click on the fifth one. So LinkedIn would try to analyze what so let's say what profession this person has, what number of connections this person has, and these kinds of things, and then maybe in future it would take those features to enhance the ranking. So machine learning is basically used in scoring. Okay, so one question is, does LinkedIn give its API to third party? Yes, LinkedIn API is present for use. You can make RESTly calls and use it. But obviously, like there would be some restriction per second or per minute, which I'm not really aware of. So just Google search for LinkedIn API. It is available for everyone to use. Yes, LinkedIn. So other question is, does LinkedIn allow external crawler to go through its site? So yeah, so there are some, so LinkedIn actually wants external crawlers like Google to get its, get its pages, because otherwise, so if you type any name, you would see that first on Google, you would see that first few results are from like many times they are from LinkedIn, and why would not LinkedIn want that, right? So so there is something called as public profile. So even if you're not logged into LinkedIn, you can see those public profiles, uh, and there are like a lot of pages, lots of articles, and there are many public pages which you don't need to be logged in. So all the data which is public, LinkedIn allows Google crawlers and other crawlers to crawl them. So now there is a question, how to get an internship at LinkedIn. So, okay. So LinkedIn is a very small company in India. It has like around 200 engineers, not more than that. And that too, they don't hire much interns. They hire like around 10 interns each year, and they give them PPOs, and that's how they hire people. That's how they hire fresh graduates, and their focus is not on hiring fresh graduates at all. So generally what happens is they would go to your college, and then they would take some online tests, etc., and they would take your interviews, and they hire interns. You might, so if there are job openings on LinkedIn, you can actually apply through that, and they might consider it. So one more question is how to display only colleges people when we register how to display only colleges people in LinkedIn. Okay, so I think the question is how to display people who are studying in a university on LinkedIn. So yeah, so you can just, like I did right now, I just typed Bits Pilani, and you can use the filters, etc., to get whatever information you want, and just go through the LinkedIn help pages. I guess you will find the solution there. What algorithm is used for page ranking? So page rank is itself an algorithm. It's not, yeah, so page rank is itself an algorithm, but there are several different implementations of page ranking. So I'm not a good authority to talk about page ranking, because as I said that page ranking is used in things which, like, network based if the documents are searched on a network, then page ranking is used. So let's say in LinkedIn, if we are searching for universities on LinkedIn, those universities are not connected to each other in some way, right? So there is no point of page ranking there. Or let's say you are searching for documents, the documents are not linked to each other. But on the web, how Google searches is, like, how Google first of all gets all its document is through page rank. So in the video, as I showed, that it would be on one page, it would crawl all the links, which are getting redirected from that page, and that is how Google would get all its data. But because Google is indexing the web, so this is the fundamental difference. What LinkedIn or what other what other companies are searching in, it's their own internal data. What Google is searching for, nothing is its internal data, everything is like on the web. Okay, so page ranking makes sense there. For LinkedIn, it has its own data in-house, so like there is no need of crawling, etc. So there is no concept of page ranking in document based search. What language is used to make a crawler? So this depends. Any language can be used to do anything. You can make a crawler in Python, you can make a crawler in C, you can also make a crawler in assembly language. I mean, you can write it in anything you want, but so the companies who write crawlers, they would like think about pros and cons of different languages. And yeah, so I don't really have an answer to that, because it depends on companies, and it depends on the requirement they have.
Okay, I think we have already exceeded time. We can, Mansi, is it okay if we can have just one last question?
Yeah, no problem.
Okay. So students, one last chance to ask Mansi Gupta a question here.
Okay, so there is one more question which I missed. Let's make it the last one. So the question is, what are the latest research topics in information retrieval? So, learning to rank, like the machine learning part of it, was a hot topic some time back, like around 2 years back, 3 years back. Now people are looking at query intention. So it is, so when you are, and they are also looking at understanding the like, so let's say you type a question in Google, right? Let's say any question like, how do I study for my final exams? Let's say this question you ask. So there is a lot of work going on how to interpret such language based queries. Okay, and people who are inexperienced in using Google, or they are doing it for the first time. So there was one funny incident where one British woman actually wrote, can you please tell me something something, thank you Google. So something like that, like the whole language query itself, right? So there is a lot of work going on, understand, so making Google, or like making other search uh, engines as you talk to humans. So yeah, so getting the intention from the query is one area where there is a lot of work going on right now. Yeah.
Okay, I think that is about it, or do we have one more last question? I think going by the flow of questions that we have, Mansi, the session was amazing.
Okay. Thanks. Okay. Yeah, I can take one more question. Anyone?
Okay, I think we have this from Technical Institute.
Okay.
Okay, they have by mistakenly given it to me. Just a moment, I'll post it on your screen.
Okay. Sure, sure. Already answered this question. So all the public pages LinkedIn has, you can go and visit them, or the crawlers can crawl them. But there are some private pages. So there are different kinds of accounts on LinkedIn. So there are some pages which are only visible to the LinkedIn members if you sign up on LinkedIn. There are some pages so there are some premium accounts, there are recruiter accounts which are paid accounts. So there are some pages which are only visible to those recruiters. So that is not public data. There might be some personal information which you only want to share with your connections or friends. That is not public data. So apart from all these, LinkedIn allows crawlers to access and crawl data.
I hope that answers your question, Technical Institute. Mansi, one last question from my side, if you don't mind.
Yeah, sure.
So my question is, what is the benchmark on which LinkedIn converts a particular account into a LinkedIn influencer?
Okay, so as far as I know, it is like edit. So LinkedIn has a lot of editors. They actually like they would write some content on LinkedIn, maybe posts, etc. They would share. They would try to make that content popular. So this editorial team, they sit together and they find people who they think that they are good for becoming an influencer. And influencers is by invite only. So it is all human work, no algorithm, nothing like that. So they would just send an invite if someone wants to be an influencer, and if they agree, then they are made an influencer.
Okay, thank you very much for answering that. And I, on behalf of all the college and professors, thank you very much for sharing your time. Students, can we have a huge round of applause for Mansi Gupta here?
Thank you so much.
Thank you.
Okay, all the best. Bye-bye.
Bye.
और क्वेश्चन पूछो.
Students, a couple of minutes I would require. So I'm sure every one of you have already registered themselves as a student on the website. If not, request you to please go on to our website and register yourself as a student. Once you register, once you sign up as a student here, log in your details to avail your free certificate. I'll just give you a quick demo. So this is the student dashboard. On the right hand side, you've got your certificate. And this is the session which you just attended, that was algorithm designing by Mansi Gupta. So just click on select. Once you click on select, there will be a couple of questions from this session itself. Answer those questions and those requests will be given to the professors in the college. So all the professors who are listening to me right now, please note that you will be getting a request from the students for the certificate. Please approve it and the students can download the certificates. Besides, I would request all the students to also visit our website and have a look at the Blockstar competition. Thank you for being such a wonderful audience. Have a nice day.